Okay, today I present 3 topics. Topic 1, solve a linear system. Second topic, elementary row operations. And the third topic, if I still have time, then I will present a topic from section 2, a matrix in echelon form. Okay, now topic 1, solve a linear system. To solve a linear system, 2 steps. Two steps to solve a linear system. Okay. Number 1, transform the linear system into an upper triangular linear system. Transform the linear system into an upper triangular form. Okay, upper triangular form. Yeah. This one, okay, and then equal to the right hand side. This step, we give a term, we give a name to this step. We call it, okay, we call this what happened? We call this step forward elimination or forward phase or forward phase. Then after we have an upper triangular form, we further reduce upper triangular form into a diagonal form. This is a step 2. Then transform the upper triangular linear system into a diagonal form. Diagonal form. Okay, diagonal form. Like this. Okay, yeah, diagonal. The matrix is a diagonal matrix, and equal to right hand side to get the solution of the linear system. Okay, so 2 steps. Now in the last class, I showed you 1 example, but I didn't have time to finish that example. Now let me start with the example today. Yeah. Example 1. From the last class, solve this linear system. The second equation is x1 minus 2x2 plus x3 is 0. Negative 4x1 plus 5x2 plus 9x3 is -9. Okay. Now we perform eliminations to transform the linear system into an upper triangular form. Actually, we did this part in the last class. The tools for elimination are the following. Okay, the tools. Okay. Three operations to perform eliminations. Number one is interchange two equations. Say equation I and equation J. Interchange two equations. Yeah, this operation doesn't change the solution of a linear system. The second operation we use to do elimination is scaling. Yeah, multiply one equation by a non-zero number. Don't multiply one equation by 0. If you multiply the one equation by 0, then you change the solution of the linear system. Okay. Now C constant times some equation, say equation I, where C non-zero. Then we have a new equation. Plug in the new equation in equation I. Okay. Then operation number 3. Replacement. Right. Multiply some equation, say equation J, and then add this new equation to equation I. Some number times some equation, then add the result to equation I. We have a new equation. Put this new equation in equation I. Don't put this new equation in equation J, but in equation I. Then this operation is called, we give a name, replacement. Now this time, this number can be 0 or non-zero. Okay, these are the operations that we use to transform a linear system. In the last class, I have done the forward elimination. I got the upper triangular system this is the original one. This is the original linear system. In the last class, I did forward elimination. I got this upper triangular linear system. This is an upper triangular linear system, right? Upper triangular. See here, upper triangular. After we get upper triangular linear system, you can use back substitution to get the solution. Say plug in x free. This variable, the value is free. Plug in free in the x free of the first two equations, and then from the second equation, we can get x2. Then plug in x2 in the x2 of the first equation, then to get solution. This is a bad substitution, but I suggest backward elimination. Okay, yeah. This step is forward elimination. Okay, now I perform backward elimination. I don't use back substitution. Okay. To perform backward elimination, I start with the third equation. Okay. I start with the third equation. I use this x3 to eliminate the x3 terms above. To eliminate the x3 term in the second equation, I multiply the third equation by 4. Third equation by 4, and then add to equation 2. Then I have a new equation. Plug in the new equation in equation 2. Okay, then the third equation is not changed, but what is changed is equation 2. 4 times equation 3. Then add to equation 4, then I get this equation, x2. Negative 4x3 is gone. It's equal to 4 times number 3, 12, plus 4, 16. In this step, the first equation is not changed. 0. Yeah. Okay, now next, I use this x3 to eliminate this x3. The operation is negative 1 times equation 3 plus equation 1. Then put the result, don't put the result in equation 3, but in equation 1. Equation 1. Okay. Then I get this linear system. Equation 3 is not changed. Equation 2 not changed. But we change equation 1. Negative 1 times the third equation add to equation 1, then x3 is gone. Negative 1 times 3 plus 0, negative 3. Yeah. Then I have a new linear system. Now next, I use this x2 in the second equation to eliminate this x2 in the first equation. Then I perform positive 2 times the second equation, then add to the first equation. Let me see, let me go back to positive 2 times equation 2. Positive 2 times equation 2, then plus equation 1. Plug in this new equation in equation 1. X3 is 3, x2 is 16. X3 is 3. X2 is 16. Now, what is X1? X1 is 2 times equation 2. Add to equation 1. So negative 2 X2 is gone. X1 is 2 times 16, 32. Then add to negative 3. So 29. So X1 is 29. This linear system is a diagonal linear system. Diagonal linear system. Then I'm done with the solution. Backward elimination is done. Backward elimination is done. The solution of the linear system is X1, X2, X3. X1 is 29. X2 is 16 and 3. Yeah, you can have a check by plugging these 3 numbers into the original linear system and see whether or not the original linear system is a true statement. Okay, should be if the calculation is correct. Okay, this is the solution to the original linear system. Okay, done. Yeah, finish. Yeah, this symbol means done. Okay, solution is done. Okay. This example is from the last class. Now, second example about solving a linear system. Example 2. Example 2. Okay. Solve the linear system. The system. X2 minus 4x3 is 8. 2x1 minus 3x2 plus 2x3 is 1. 5x1 minus ax2 plus 7x3 is 1. Okay, solve this linear system. Now this time, to save some writing, I prefer to work on augmented matrix. Recall that augmented matrix contains all the information about a linear system. Okay, only just write down the variables. Okay, now work on the augmented matrix to save some writing. Okay. Augmented matrix. The first column are the coefficients of the variable x1. The first equation, low x1. Actually, there is a x1, just a 0 times x1. So I put 0 here. The 2, 1 entry is 2. The coefficient of x1 in the second equation, 2, 4, 5. Second column of the augmented matrix is the coefficients of the variable x2. 1, -3, -8. And then third equation, -4, 2, 7. Then the last column of augmented matrix is the right-hand side. 8, 1, 1. Okay. Usually we separate the right-hand side from the coefficient part by a vertical line. Okay, now let me work on this augmented matrix. Perform forward elimination. That means that I want to transform the augmented matrix into an upper triangular matrix. Because the 1-1 entry is 0, I cannot use 0 to do elimination. So let me perform switch. I switch the first two rows, row 1 and row 2, switch. Then I get 2, -3, 2, 1, 0, 1, -4, 8, 5, -8, 7, 1. Then separate the last column from the first 3 columns. Then now I use this number to eliminate 5. The operation is -5/2 times the first row. Add the result to the third row, right? Perform this operation. Then I get 2, -3, 2, 1. Also, second row is not changed. -2 times -5/2 times 2, add to 5. 5 is gone, 0. -5/2 times -3, 15/2. Then add to -8. I get -1/2. -5/2 times 2. Add to 7. I get 2. And then -5/2 times 1. Add to 1. I get -3/2. 3/2. Now separate. Yeah, separate. Yeah, this matrix is not in upper triangular form yet. Continue the elimination. Next, I use this number to eliminate this number. The operation is +1/2 times row 2 plus row 3. This is a new row. Put this new row in row 3. Then I get this matrix. Zero, 1, -4, 8, 0, 0, 0, 5/2. Forward elimination is done because the matrix is in upper triangular form. Okay? Upper triangular form. So forward elimination is done. From this augmented matrix, I can see that the linear system has no solution. Can you see that? Can you see that this augmented matrix is a linear system? This linear system has no solution. Why? Anyone can tell me why? I can see that no solution. Can you see that?
There's no solution for x3.
You mean the third equation, right?
Yeah, sure.
Yeah. Take a look at the third equation. Okay. Let me write this augmented matrix in equations. In equations, the final augmented matrix is the following linear system. Okay. One row is an equation. The first row is the equation x1 times 1 times x1, right? The 1 entry here. Coefficient of x1. This is the coefficient of x2 minus 3/2 x2 plus x3. Then the last entry is right hand side, 1/2. This is row 1 of this augmented matrix. It is this equation. Now, second row. Second row is the following equation. 0 times x1, 1 times x2. So x2 here minus 4 times x3 is 8. The third row is this equation. 0 times x1, 0 times x2, 0 times x3 is equal to 5/2. That is the third equation. So the equation is this. In details, it is a 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 5/2. Because of the third equation is level 2, no matter how you assign values into x1, x2, x3, you cannot make the third equation a true statement, right? 0, of course, is not 5/2. So no solution. The original linear system has no solution because of the third equation here. Third equation here. 0 is not equal to 5/2. So no solution. We don't need to perform backward elimination to find the solution. Okay. Yeah, done. Solution is done to this linear system. Done. Done. Okay. Now, example 3. I still use this linear system, but I change this number. Let me change this number from 7 to 6, okay, and solve the linear system again. Example 3. Solve this linear system. x2 minus 4x3 is 8. 2x1 minus 3x2 plus 2x3 is 1. Then 5x1 minus 8x2 plus 6, not 7. x3 is 1. Now this time, this new linear system has a solution. Again, let me work on the augmented matrix of the linear system. 0, 1, -4, 8, 2, -3, 2, 1, 5, 1, augmented matrix. Coefficient matrix plus the right-hand side, augmented matrix. This matrix contains all the information about the linear system. Each row is an equation. Again, let me switch the first 2 rows. 2, 3, 2, 1, 0, 1, -4, 8, 5, 8, 6, 1. And then according to my notes, I scale the first row first. 1/2 times first row. Then put the new row in the first row, scaling. 1, -3/2, 1, 1/2. And then 0, 1, -4, 8, 5, 1. Scaling. Because I don't want to work with a fraction. Now I use this number to eliminate this number. Usually, we call this number a pivot number because I use it to eliminate the numbers below. To eliminate the number 5, I let -5 times first row, then add the result to row 3. -5 times first row plus row 3. This is a new row. I put the new row in row 3. Don't put the new row in row 1. Then I get 1, -3/2, 1, 1/2. Second row is not changed. The third row, 0, 5 is gone. -1/2, 1, -3/2. I am performing forward elimination. I want to reduce the matrix into upper triangular form. Next, I use this number to eliminate -1/2. The bulk calls this number pivot number. Pivot number. Okay. To do that, +1/2 times row 2 plus row 3. Put the new row, put the result in row 3. We call this operation replacement. Then I get 1, -3/2, 1, 1/2, 0, 1, -4, 8. The third row becomes 0, 0, -1, 5, 1/2. Now I am done with forward elimination because this matrix is in upper triangular form. I'm done. Okay. Here you can get the solution by back substitution, but I don't like back substitution. I prefer backward elimination. Now I perform backward elimination. To perform backward elimination, I start with the third row. I use this number, -1, to eliminate the numbers above. So -1 is a pivot number or pivot entry. To eliminate the number 4, I multiply the third row by -4 and then add to -2. Yeah, add to -2. Row 1 is not changed. Row 2 now is changed. -4 is gone. -2 times 5/2 plus 8 is -2. Row 3 not change. Not change. Okay. Next, I use this number again to eliminate this number 1. The operation is 1 times row 3 plus row 1. Then put the result, put this result in row 1. Don't put it in row 3. Then I get this matrix. 0, number 3, 0, 1, 0, -2, 0, 0, -1, 5/2. Separate the last column. Backward elimination, I want to make the matrix into a diagonal form. This matrix is still not in diagonal yet. Next, I use this number to eliminate this number. So the number 1 is a pivot number. The operation is 3/2 times row 2, add to row 1, put the result in row 1. Then I get 1, 0, 0, 0, 0, 1, 0, -2, 0, 0, -1, 5/2. Now, backward elimination is done. Because this matrix is in diagonal form. In equations, the final augmented matrix, augmented matrix, yeah, the final, yeah, I mean this augmented matrix is the linear system. First row is 1 times x1. 1 times x1, then 0 times x2 plus 0 times x3. Right-hand side is 0. Second row is 0 times x1 plus 1 times x2 plus 0 times x3. Right-hand side, -2. The third row is -3, is 5/2. Now, from this diagonal linear system, we have the solution of the linear system is x1, x2, x3. x1 is 0, x2 is -2. How about x3? x3 is -5/2. -5/2. Done. Finish. This is the solution of the linear system. Example 3. Then the next example is example 4. Example 4. Determine the values, maybe more than one value of h, such that the following matrix is the augmented matrix of a consistent linear system. Again, consistent linear system means the linear system has at least one solution, one or infinite many solutions. The linear system is called consistent. If a linear system has no solution, we call that linear system inconsistent linear system. The matrix is 1, H, 4, 3, 6, 8. This matrix is augmented matrix of a linear system. So the last column is right-hand side. Let me separate the last column from the first two columns by a line. To answer a question of this time, forward elimination is sufficient to answer a question of this time. To answer a question about whether or not a given linear system has a solution, forward elimination is enough. You don't need to perform backward elimination. Now let me perform forward elimination on this augmented matrix. 1, H, 4, 3, 6, 8. Solve this linear system. Two phases, forward phase, backward phase. Okay, now forward phase. I use this number to eliminate the number 3. So this number is a pivot number. To eliminate the number 3, negative 3 times row 1 plus row 2. Put the result in row 2. This operation doesn't change row 1. 3 times negative 3 times 1 add to 3. 0. Negative 3 times h add to 6. I get 6 minus 3h. Negative 3 times 4, negative 12 plus 8, negative 4. Forward elimination is done because this matrix is in upper triangular form. Now I can answer the question, what values of h make the linear system has solution? Okay, first, when this number, let me use green color. When this number is 0, the second row is the equation 0 is equal to negative 4. In this case, the linear system has no solution. When this number 6 minus 3h is equal to 0, namely, h is 2, right? H is 2, then 6 minus 3h is 0. When h is 2, the linear system has no solution. Why? Because plotting 2 in h, then we get 1, 2, 4, 0, 0, negative 4, right? The second row is second row is this linear system. 0 times x1 plus 0 times x2 is negative 4. This equation is never true for any values of x1, x2. So when h is 2, the linear system has no solution. How about other values? Second case. When 6 minus 3h log 0, namely h not equal to 2. In this case, then the linear system has solutions. The linear system, let me copy this upper triangular matrix here. 1, h, 4, 0, 6, minus 3h, negative 4. Now, this number non-zero. In equations, this augmented matrix is x1 plus h, x2 is 4. Second row is non-zero number times x2 is negative 4. This linear system has a solution. Why has a solution? Solve it. from the second equation, I get h is -4. 6 minus 3h. Because 6 minus 3h non-zero, I can divide the equation by a non-zero number. This is x2. Now, plug in this number. Plug in this number in the x2 here. Plus h times -4, 6 minus 3h is equal to 4. Now, the solution is x1 is 4 minus h, -4, 6, 3h. x2 is, so when h is not equal to 2, the linear system has one solution, exactly one solution. So the answer to this question is determine the value of h such that this linear system has solution. The answer is there are infinitely many values. Okay, provided that h is not equal to 2. When h is not equal to 2, this linear system has solution. That is the answer. Done. Finish. Yeah, this is topic 1. Today, second topic. What second topic is? Elementary row operations. Topic number 2. Still section 1.1. Elementary row operations. Okay. The following 3 operations are often used to transform a matrix into another matrix. These 3 operations, the book calls them, we call them elementary row operations. Okay. Okay. 3 operations. Operation number 1. Interchange 2 rows. Row I and row J. Switch 2 rows in the matrix. This is very similar to switch 2 equations of a linear system. But a matrix, you can view a matrix as a linear system, or you can view a matrix as just a matrix, not a linear system. Interchange 2 rows. Second operation, scaling. Some non-zero number times some row. Then put the new row in row I. Here, C non-zero, very important. Don't multiply one row of a matrix by 0. Okay. The third operation, replacement. some number times some row, say row J, plus row I. Put the result in row I. Don't put the result in row J. Now this time, C can be 0, can be non-zero. These three operations are called elementary row operations. We often use these three operations transform a matrix to simplify a matrix. Next, let me introduce a term. Let me call this definition. Two matrices A and B are said to be just a term, row equivalent. Notation is denoted by A tilde B. A tilde B means these two matrices are row equivalent. What it means, row equivalent? If one matrix can be transformed into the other matrix by a sequence of elementary row operations. Whenever two matrices, can be transformed by elementary row operations from one to the other. These two matrices, we call them row equivalent. For example, this matrix and this matrix they are row equivalent. And why? Because I can perform this operation on the matrix A. I let -2 times row 2 plus row 3. -2 times row 2. Then add it to row 3. Yeah, put the result in row 3. Then I get 1, 3, 4. 0, -2 times -2, 4, add to -5, so -1. -2 times 6, -12, plus 10, -2. Yeah, so this is a B. Therefore, according to the definition, these two matrices are row equivalent. Row equivalent. Okay. The third topic today. Let me see. What is the third topic? Here. The third topic belongs to section 2. A matrix in epsilon form. What it means? Epsilon form. Epsilon form, step-like form, or a step. Epsilon. Step-like form or staircase structure. Say, for example, this matrix 0, 0, 1, 2, 3, 0, 0, 0, 4, 5, 0, 0, 0, 0, 6. Yeah. This matrix is in epsilon form. Epsilon form. You see? Step-like pattern. Yeah. Okay, precisely, let me present the precise definition of epsilon form. Topic number 3. A matrix. This is a section 1.2. A matrix in epsilon form. Okay. Precisely, the definition is here. Definition. Okay. A matrix in epsilon form. Okay. Has the following 3 properties. Okay. A, or the non-zero rows are above, should be above any row of all zeros. Say, for example, okay, let me write a matrix in epsilon form. 0, 1, 2, 3, 4, 5, 0, 0, 0, 7, 8, 9, 0, 0, 0, 0, 0, 10. Yeah. Let me add one more row. Erase. Yeah. I say 0, 0, 0, 0, 0, 0. Yeah. Okay. All the non-zero rows are above any row of all zeros. Yeah, the last row is a row of all zeros. Row 1, non-zero row. Whenever a row has a non-zero entry, that row is called non-zero row. So first row, non-zero. Second row, non-zero. The third row, non-zero, because the last entry is 10, not 0. So this matrix actually is in epsilon form. All the non-zero rows are above any row of all zeros. Now, property number 2. The leading entry of a row should be in a column to the right of the leading entry of the row above it. Okay, take a look at this example. The first row leading entry is 1. Second row leading entry is 7. Third row leading entry is 10. The fourth row, low leading entry. Property B says that leading entry of a row, say for example, consider the second row, leading entry is 7. The leading entry of a row, say for example 7, in a column, in this column, in a column to the right of the leading entry of the row above it. Row above the second row is row 1. In a column to the right, yes, of the leading entry of row 1. Yes, this column is to the right of the leading entry of row 1. This is one example. Now, property number 3. All entries in a column below a leading entry are zeros. If a matrix has these properties, then the matrix is called in epsilon form. About property C, take a look at this example. All the entries in a column below a leading entry. Say, for example, row 1, the leading entry is 1. All the entries below 1 are 0. 0. Row 2, leading entry is 7. All the entries below 7 are 0. 10 is the leading entry of row 3. All the entries below 10 are zeros. So this matrix satisfies all these 3 properties. Therefore, this matrix is in epsilon form. Basically, epsilon form is a step-like form. I will continue with this topic 3, in next class. Okay, let me finish today's class here.